So my problem is runner number 106 had stopped for water only 50 meters away from the finish line. During his break, he notices runner 224 is 24 meters in front of him, going 4 meters per second. If runner number 106 starts running immediately and can accelerate at 2 meters per second squared to his fastest speed of 5 meters per second and be constant at that speed. So first we would have to start off by drawing a diagram. So let's say runner number 106 is here at his break, and here would be runner number 224, and he's still going the constant velocity towards the finish line. And we know that runner number 224 is 24 meters in front of runner number 106, so this would be 24. And he's 50 meters from the finish line, so this total would be 50, leaving this 26 meters because 50 minus 24 is 26. So if we were to have number 224 here, we know that he is going a constant 4 meters per second as his velocity, and runner number 106 is over here, and we know he accelerates at 2 meters per second squared until he gets to 5 meters per second and is constant towards the finish line. So first we're going to start with runner number 106, and we need to find the time it takes for him to accelerate up to 5 meters per second. So we can solve for t by doing the final velocity minus the initial velocity over the acceleration. So we know that his final velocity will be 5 meters per second, and his initial is 0 because he's on the break, he's not moving, and his acceleration is 2 meters per second squared. So that would come to 5 over 2, which would be 2.5 seconds. So we need to plug that into the displacement formula to figure out how long of a distance it took to accelerate at that time. So you would plug into the displacement formula, velocity times time plus 1/2 acceleration t squared. So we know the initial velocity is 0 plus 1/2 times the acceleration, which is 2, times the 2.5 squared seconds. And when you do the math out, it would equal 6.25 meters. So it takes him 6.25 meters just to get to 5 meters per second. So now you have to figure out how the time it takes for him to go 5 meters per second at that constant velocity. So the whole distance is 50, so you would subtract the 6.25 meters from the 50 and get 43.75 meters. And then the acceleration would be 0 because it's a constant velocity, so the final velocity and the initial velocity would both be 5, so 5 minus 5 would be 0. So you don't need to worry about the second half of the equation, just the first. So the initial velocity would be 5 times the time, which is what you're solving for. And when you divide 43.75 divided by 5 would be 8.75 seconds. And you need to add the 2.5 seconds it took just to accelerate up to that speed. So those two added together is 11.25 seconds. So it takes runner number 106 11.25 seconds to get to the finish line. So for number 224, we know that he's going a constant acceleration of 4 meters per second. So if we were to solve for the acceleration, it would be 4 minus 4 over the time. And either way, that would be 0, because like over here, the 4 minus 4 is 0. And so the acceleration as a whole would be 0. So like we had over here, this whole part would just equal 0. So we know how far he had to go until he reached the finish line, which is 26 meters. So we would plug this into the displacement formula. So the 26 meters equals, and we know the initial velocity, which is 4 meters per second, and we're solving for time. So we would just divide 26 by 4 to get 6.5 seconds as the time. So since the time of runner number 224 is shorter than runner number 106's, it'll take him a shorter time to get to the finish line, which means that no runner number 106 will not win the race, because this is obviously faster than this.